Hello, welcome everybody to this second installment of this second series of the MixGen, where we like to bring together young researchers with more experienced ones to have the possibility to have a meaningful scientific interaction. We always like to organize these events in two parts. A first part with a talk by a more experienced researcher, and then some young ones. And then a second part where we move, for those registered to the event, to a gather room where we can, participants will be able to present posters and also have the possibility to interact more informally among all the participants to the event. We think this is a good environment, especially the current situation, to also facilitate and encourage communication and the possibility of scientific exchange for younger researchers in our community. Today, we have the topic will be about machine learning and simulations. And as I say, now we will start the first part. This is basically, we have an experienced researcher, Gabor Chani, from University of Cambridge. And visible, we had also invited Thorben Fröhling from CISA and Sylvia Bonfanti from Università degli Studi di Milano. Unfortunately, Thorben, due to a last-minute personal emergency, will not be able to join us, but I'm very happy to have Gabor and Sylvia. Before we move on to the first presentation, I would like to go briefly give you a couple of general points about how we should organize ourselves in this online session. So first of all, the meeting will be recorded, and actually then it will be made available on the Sgdma YouTube channel. Actually, in our Sgdma YouTube, we have a list where you can actually look at all the past MixGen sessions. With respect to how we will interact, at Sgdma we like promoting as much as possible interaction among all participants, and being remote is a challenge. For the first talk that is more extended, actually you can ask questions during Gabor's presentation. You can do that using the chat channel. You can write down the question, and then I will be in charge of relaying it to Gabor at convenient times during the presentation. And at the end of the presentation, there will be then a more open or general Q&A session, where then you can simply indicate through the chat that you want to ask a question, write or with a hand or in any way that I will see it, and then we will unmute you so that then you can actually post the question directly. And also, depending on how the answer goes, that also gives the possibility for a more elaborate or a certain dialogue between the speakers and the participants. So that will be like the second main Q&A. In the case of the second talk by Sylvia, because it's shorter, then I will not take questions during her presentation, and then the Q&A will proceed exactly in the same way. You indicate simply that you want to ask a question, we unmute you. You will see the possibility that you can unmute, and then you can ask the question in the same way. So just to be sure, you will receive the notification that to mute, and then you mute yourself. You cannot activate the video, and then everything is through Q&A, so there is no chatting also among participants. I would like then to mention, also take the opportunity here to tell you about the next events that will take place online until the end of the year. In a couple of weeks, in December 9th, we will have another installment of the series, the Sgdma Model Classic series. This is also an event where we invite those scientists who have developed algorithms that have become a reference for the community, so that they can tell us about the scientific process that was behind the proposal and the development of the algorithm. What did it bring to the community, how it has evolved, And then there is a second part that is more an informal conversation to also get to know how this science around these algorithms was developed in a more personal level beyond the usual exchanges that we have in scientific meetings. So this next installment will be on fluid phase equilibria by computer simulations, and the two invited lecturers are Thanos Panagiotopoulos and Dominic Tildesley. That will be in the afternoon on Thursday, December 9th, so you are invited. And again, on our website, you can look at previous lectures, so you can have a flavor of how these events work. And also, just before Christmas, the Christmas break, we will have another installment of the mixed gen sessions. This will be done in that case. In this case, the topic will be about simulating colloidal systems. The experienced speaker will be Emanuela Zaccarelli, and now we will be opening to receive participants and posters. So you are again welcome to participate. And you can also register on our webinars mailing list, as indicating at the top of the webpage, so that you can also keep. We announce all these events as they will be happening also during next year, in case you want to be updated. So with this, I finished. So let's start the session. And as I said, in this first part of today's session, the first talk will be given by Gabor Chani in a structured presentation where some of his collaborators will also contribute. And please, we are really looking forward. So now the floor is yours, Gabor.
Thank you very much. It's a huge pleasure to take part in a CCAM activity of a new kind. I think it was brought on by the necessities of being apart, and yeah, we can be together here. So that's great. Do you see my screen? Is it working?
Yes, we can see it. Yeah.
We are also projecting it out here for all of us here in this room. So yes, thank you. And the talk will be about the kind of machine learning that we do here, which is to create force fields. And I call them first principles force fields, which I will explain in a minute. And the title is Status and Challenges. So this is a very much reused old slide whose meaning for me has changed over the years. But it's very familiar to many of you. It lists the pictures refer to different kinds of techniques with which we model materials, all the way on the left from quantum chemistry, where we essentially attempt to exactly solve the Schrödinger equation for electrons and nuclei, all the way up on the right to some coarse-grained molecular modeling. I sometimes have an even further length scale, continuum modeling length scale, but not today. The axes are, on the horizontal axis, we have capability in terms of atoms, in terms of simulation time. For linear scaling methods, it makes sense to think about the product of the two. But on the vertical axis, I have it's a rather provocative axis. It's called accuracy, and rather provocative numbers. But you can see that what matters is the orders of magnitude. So I say that quantum chemistry has, in principle, an accuracy, an error of 0. So exact accuracy if we push it hard enough for small enough systems. But as we go up through these length scales and different techniques, then the typical accuracies that we can reach really dramatically drop. So where for interatomic potentials, force fields, I put qualitative, because although in some cases you can assess their accuracy quantitatively, in many situations they just give you complete nonsense. They're not designed to capture many situations, so hence this qualitative label. So how are these models made? So typically they're made sort of in pairs or somehow top down. When you have a theory of how the world works, let's say how one of these large systems for which you want to model with the coarse-grained molecular level, either liquid or something like that, soft matter, then you have a theory about how it works. You create a very parsimonious, simple model that explains the phenomena, and then you test it. And that loop goes around. So if it doesn't work, then you refine your theory, and so on. And this idea goes all the way down. So if you want to know how molecules work, then you have a theory about that, about how atoms come together to make molecules. You test it, and then again, you iterate this closed loop. And this really happens all the way through. The alternative to this is first principles modeling. So it's more of a deductive approach. And this is where I'm appropriating the word first principles, or rather returning it to its original meaning. If you check out the materials modeling literature, really first principles modeling is a synonym for electronic structure theory. But I don't think that's right. I think first principles modeling is really an idea that you start from quantum chemistry, start from the Schrödinger equation, which is true, and then you go up from there. You deduce things from there. You approximate in a controlled manner and deduce how higher length scale behavior happens. And so why is it that in practice first principles modeling has been basically made a synonym of electronic structure? It's because of this empiricism that appears with force fields and interatomic potentials. Because up to the crudest quantum mechanics, we feel that we are treating electrons, we're treating the system in some systematic, controllable way, and that idea just is stopped. And that's what I really want to change. And that's all the more, right, so this is where you stop treating electrons, is essentially where first principles modeling used to stop. But that's very odd, really, because if you look at how computer time is spent, almost all the computer time in terms of fraction of large supercomputing centers is spent doing what is called first principles molecular dynamics, so ab initio molecular dynamics. And that is a very, very wasteful thing to do, because you're actually asking questions about atoms and where they are, and you sample some distribution of the total energy, atomic energy of the system. But yet you do that every step, you do some kind of electronic structure calculation. You're asking questions at the wrong level. So really what I'd like to do is to change that and extend this first principles modeling approach as it should be done with the same philosophy all the way up to the atomic scale, to deduce interatomic potentials and force fields from electronic structure rather than write them down empirically. And of course, the idea can be carried further, maybe to much, much higher length scales. So this work is not just me, but the small field of people who thought this started really, or got a very big boost about more than 10 years ago. No, I was going to say 10, but it's about 12, 13 years ago, with this pair of papers. And we sort of made a promise, I think, to the community. The first paper is by Jörg Behler and Michele Parnello, Generalized Neural Network Representation of High-Dimensional Potential Energy Surfaces. And the second one from my group, Gaussian Approximation Potentials. The accuracy of quantum mechanics, but without the electrons. And of course, by accuracy, I mean here the force field accuracy. So retaining the accuracy for the atoms, but without doing actually electrons. These two approaches are actually rather similar from where we are standing now, 15 years later. Jörg Behler used the neural network regressor, which is mathematically which looks quite different, but mathematically it's quite close to the kernel regression approach, linear fitting approach that we used in this paper here. I put the formulas up there, linear algebra, these quantities are matrices. And about a decade later, in 2020, I wrote on this slide that the message is that this promise has been fulfilled and this problem has been solved. And of course, the quotes around here are part of our sometimes false, sometimes not false modesty, depending on the mode of speech. But of course, what we mean by solved is that science is being done in this new way. There are rigorous, controllable approximations to the electronic structure on the atomic scale. That doesn't mean that they can't be better. So of course, they can be improved, and better solutions are possible and indeed desirable. And some of the topics that we'll bring up today will be in that direction. But there is really a new kind of materials modeling problem and materials modeling task that has been invented here. People are being trained in it, and there is really a new type of material simulation that is increasingly being carried out. So in the next few minutes, I want to tell you sort of what happened in the last 15 years, how this came about. So first, just an illustration that it really worked. So we have applications now to carbon, silicon, and boron, phosphorus, and then to more complex materials, gallium oxide, hafnium oxide, and the last one here is an iron sulfur compound at Earth's core conditions. These are just papers from my group, but there's really been an explosion, a proliferation of wide proliferation of work in this direction. These are all controllable force fields fit to electronic structure, operating on a large scale and doing science that you couldn't do before. So there are two components to this. The first one is function fitting. How do you fit a function? The potential energy of atoms is a function of their coordinates. It's a very complicated function, and we have to learn to take data and fit that function. So there is a long history, even within materials modeling, let alone wider numerical analysis of function fitting. But within, for materials and molecules, people have used analytical fits to potential energy surfaces of small molecules for many decades. And a lot of the quality, the ways that has been done kind of comes back in our work, but principally this has been restricted to small molecules. And we sort of now understand why and how those limits can be transcended. Of course, there were empirical force fields, and one can see them now as a high-dimensional fitting exercise, but they weren't systematic, and hence that's the big change. And what happened in the last 15 years is that we've learned to use kernel machines, feed-forward neural networks, and more recently symmetric polynomials. That's the new stuff, and they kind of subsume in a way the earlier methods, the earlier work. So where we arrive now is, at least in my mind, I understand all of these methods through this lens of expanding an atomic neighbor environment through symmetric polynomials. And we now think that this is how body-ordered force field terms of the old empirical force fields should be understood. It's also very, very close to the analytical full potential energy surface, the PIPs, the permutation invariant polynomials of Bowman and Brahms from 20 years ago, is somehow very closely connected to what we do now. The kernels and shallow neural networks that we started out with 10 years ago can be also cast in this form. And even the newest methods that are coming out in the last couple of years, you might have come across them, equivariant message passing neural networks, a different kind of neural network fit than the shallow feed-forward ones, can also be linked through this lens of symmetric polynomials. The other ingredient is local representation. So when you have a bunch of atoms, you want to create a function of their energies, but you need to describe the inputs, the environment of those atoms. And starting out with those pair of papers, the community has given rise to a bewildering array of different representations, everybody bringing out new ideas in the last over the last 15 years. And one of the real gratifying things was not just understanding how the regression methods are very similar to each other, but also how the representations, all these different acronyms, belong to different, come up at different results of different papers, and they all are very, very related. So it really is to do with how you impose symmetry onto representation. So you have Cartesian coordinates, which is how the data comes eventually. That's atoms are somewhere, but the representations that we create need to be symmetric with respect to rotation and permutation and translation. And depending on how you impose those symmetries, in which order do you impose them onto Cartesian coordinates, that's how this tree is created. So if you first implement rotational symmetry, essentially you have internal coordinates, distances, angles, and so on. And then once on top of that, you have different ways of implementing permutational symmetry, and that gives rise to this array of descriptors. If you go in a completely different direction and take the Cartesian coordinates and first impose permutational symmetry, then you have atom density fields. So you have a scalar field of what atoms are around you, and then that's not yet rotationally symmetric. And depending on how you impose rotational symmetry, you get a range of different descriptors from that. And the really cool thing is that this way of looking at things through this lens of symmetry, of how you impose symmetry onto coordinates, actually gives rise to this idea of many-body correlations, describing the atomic neighborhood via correlation functions, and that is very closely connected to how one constructs polynomials that obey these symmetries. So let me just show you a couple of examples, a couple of successes that I'm very proud of, which really 15 years ago, I didn't know that this sort of thing would be possible ever. So this is in some sense lucky. It tells us something about Schrödinger equation and its solutions and quantum mechanics and the relevant part of the materials configuration space, that we can actually fit these very complicated potential energy surfaces. So the first example is carbon, which we started to work with back in 2016, but this is a more recent iteration of a carbon potential. And imagine that here is a representation of all the different carbon structures that you can find if you scour papers and databases online. So it has diamond structures in various forms, amorphous carbons, graphites, nanotubes, fullerenes, and so on. And you're trying to make a potential that fits to some reference data. Let's say you pick a density functional theory that is appropriate for this sort of system, and you want to create a potential that fits within some required accuracy onto all of these structures. That in itself is a very, very hard task. Let me illustrate that on the example of just the carbon dimer and graphite layers. And pay attention to the energy scales. So if I want to describe a carbon dimer, so the red here is DFT and the black is our fit. But if I want carbon dimers to repel each other as the two atoms come close, I need to be able to describe potential energies that are on the order of 10 EVs. The Y scale here is in electron volts. And yet on the other side, if I also want the same potential to give me the very weak van der Waals binding of between graphite layers, then the energy scale of that is 0.1 EV per atom. So if you want accuracy, we need, let's say, another factor of 10 here. So really we're looking at 0.01 accuracy EV over here and 10 EV over here. So we need an accuracy of 1 part in 10 to the 4. And that is over a very large configuration space. And that is a very big fitting, very, very, very challenging fitting task. But it works, so we can do it. This particular fit was done with 9,000 basis functions. There are 6,000 DFT calculations that went into it. Of course, many of them were large with many atoms. So altogether, there are about 400,000 scalars, so energies, forces, and stresses. And because the fit doesn't deal with electrons after it's done, it's a force field, the speed ups that you get with respect to DFT on moderate sized unit cells, where you can still measure the DFT speed, is greater than 1 million. So we've created a model for forces for carbon atoms that is 1 part in 10 to the 4 accurate with respect to DFT and is 1 million times faster. And just other than, of course, point-wise accuracy is just the beginning. You actually want material properties. And the next step is to look at formation energies of defects and other structures. So here's a typical example of what these kind of plots look like. So each point here, each column here on the horizontal axis is one kind of defect in a carbon structure, and the targets are the black circles, the model, this machine learned interatomic potential is the red crosses, and you can see that the trends are really very good. And just for comparison, the gray crosses are previous empirical models of carbon. Some of them are okay for some things, others are less so. But it's not controllable. It is generally quite a mess. So we've gone from this empirical, non-systematic situation to a controllable fit where we can approach the accuracy as we like. What is such a model good for? One of the areas where we've had a lot of success with this is amorphous systems. So amorphous carbon is a technological material. But it's very, very difficult to simulate, because what is it? What is the structure? Show me a unit cell of amorphous carbon. Even that question, what does it actually look like on the microscopic scale, is not clear. What I'm showing you here is something more complicated. Is the Young's modulus. That's something that one can measure experimentally. And of course, not only do you have to have the right structures in the computer if you're going to predict that Young's modulus, but then it has to have the right dynamics, the right relaxation properties. As you pull on an amorphous material, there's a lot of relaxation that's concurrent with that. So what you see here are the experimental points in these triangles, and really the best model before the machine learned data-driven solution is this black one here, and it's overestimating the Young modulus by a factor of 2, and our model is the first that basically gets it right. People have taken these models, and that's really I would say the benchmark for creating force fields is, does someone else use them? And here's a very big recent survey of carbon models for amorphous carbon, and what you see here are very slow and careful quenches of very large 30,000 atom unit cells. And you can see the variety. This is at 1.5 grams per cubic centimeter. This is at 3.0. And the different empirical force fields give rise to very different microstructures. Now, of course, this is something that is a pure prediction. We can't do this with DFT. It's very hard to get experimental information about the structure. So what we see here is that the Sgdma model behaves on the low density side somewhat similar to EDIP in terms of its amount of curvature and the amount of empty space that it has. And at 3 grams, it is quite different from any of them. It actually phase separates, and this is a mixture of tetrahedral amorphous carbon and sort of highly graphitized layers. When you have a good model of amorphous carbon, you can do things that are actually technologically relevant. So this is this work carried out by Miguel Caro and Volker Deringer is about simulating the growth of tetrahedral amorphous carbon. So this is where you have an incident ion and you grow a film, so essentially atom by atom. And it's been known for a very long time that when you do this in a wide range of energy of the incident ion, you get this very high density amorphous carbon film. And when people have tried to reproduce this with potentials, it really didn't work. So no empirical potential is able to reproduce this high percentage, 90% sp3 carbon. And when we tried it with our model, it really worked. It really worked. So what you're seeing here is a movie of each frame of this movie is one atom having come down at this incident ion energy and relaxed into this structure in a couple of picoseconds. We take away the heat, and then we throw another atom. And what you see on the right is the analysis of the structure as a function of depth. And we separate the sp, sp2, and sp3 fraction. And what you see here is that the stationary state of this growing film is the 90% sp3 carbon that is observed experimentally. And we see how that comes about. So the top of this film is mostly sp2 with some sp chains sort of at the very top. But as the film grows, those structures stay on the top, and the bulk of the film becomes sp3. And there's been a lot of debate about the mechanisms that the microscopic mechanisms that lead to that sp3 densification, and one can scrutinize this simulation and find out what the actual mechanism is. Here's another example, again sticking with amorphous science. This is amorphous silicon under pressure. So it's been known experimentally that if you take amorphous silicon, then unusually when you crush it under high pressure, it actually then crystallizes. So the order increases. But the mechanism of that crystallization and how you go from a principally tetrahedral amorphous carbon at ambient pressure to an 8-coordinated simple hexagonal crystal wasn't known, because it's hard to get this sort of dynamical information from experiments. So here's a machine learned gap model fitted to DFT, but run on a length scale, which is very much outside DFT's capabilities. So this is 100,000 atoms, and we simulate a 200 picosecond compression. The color coding here is the neighbor count, start from 4 up to 8 and then higher, because what we see is that, you can see this in the images that I pulled out of this simulation, is that when the structure collapses in its volume, you actually get these, half the atoms have coordination over 10. So it collapses into this essentially closed pack structure. And then over tens of picoseconds, you get the recrystallization into the simple hexagonal 8-fold coordination. And we can do more than just structure. So we fitted a machine learned model that gives us the electronic density of states, because that is an electronic property of the local structure, which again, one can regress. And what you see here is, as a function of pressure, how this pseudo gap disappears. So as the structure densifies and changes the local structure, that's when you see this semiconductor turn into a metal. So this is a good moment to ask if there are any questions. I don't actually see the Q&A at this point, but if there are any questions.
So far, there are no questions in the, I remind you, you can.
I've been going quite slowly.
So let me. Q&A if you, and I will relay, but so far there are no questions. Okay. Please.
So, so I've given you the vision, I've given you some successes, but how do we actually do this? And there are really 3 components, as I mentioned before. There's representation, regression, and the third one is the application of what you actually do with these fitted models. And I'm going to talk about a little bit about the representation and a little bit about the regression, and then talk a little bit about how actually do the fitting, this sort of closed loop cycle of taking DFT data, making a fit, using the representation that we choose and the regression, then trying out that potential entry surface, and then if it's not good enough, then we go back and we iterate. I'll touch upon that as well. So let's go back to the beginning. So this is work that's 10 years old. That's, for us, this is what started us on the road to success. And this is really, how do we represent in a symmetric way the neighborhood of an atom? And we call this the SOAP representation, for reasons which will become clear in a moment. So we start by taking an atom I and looking at its neighbors and putting a small Gaussian or a delta function, depending on which implementation one chooses. But very early on, we went down the little Gaussian route. You place the little Gaussian and you construct what we call a neighbor density around the atom with a cutoff. So there's a smooth cutoff that takes this density down to 0 as the atoms go across a boundary. And this density is therefore permutationally invariant because we sum over all the neighbors. It's smooth and it's continuous with respect to moving the atoms. but it's not rotational invariant. To ensure rotational invariance, we turn to the oldest trick in the physicist's book, which is expanding in YLMs. So you take the density and expand it. You pick a radial basis, GNR, and YLMs for the angular part, and you write this density in that basis with some basis expansion coefficients, C and LM. The N and the L are the radial and the angular channel indices, and the M is again the index, second index of the YLM. And it turns out that if you take this product of these C's and sum over M, so C dagger C and LM, C N prime LM, the N and N prime don't have to be the same, but the L does. If you sum over this product over M, then you construct this 3-index object, P and N prime L, and we call this the power spectrum, and this is rotationally invariant. The reason we called it so is because the way it was originally derived is that if you take two different environments, the unprime and the prime, and you consider the dot product of these P's, it turns out that that is the same as this complicated expression. But if you sort of go inside out, you take the two densities, you multiply them together, then you integrate them with respect to space, and then you also integrate this product over all possible rotations in 3 dimensions. That's the R hat. So each R hat is a rotation. You rotate one of the environments, and you do this. These two integrals, they are each 3-dimensional. So this is a 6-dimensional integral, and that we thought at the time was a very good way to compare environments. That was a good way to say when two environments are similar to one another. And it turns out that this thing is analytically equal to P dot P prime, where P is defined here, if you take a complete basis. So this is why.
Yeah.
Is there a question?
Yeah, there is a question from Johnny. He would like to know how this cutoff is chosen, and I guess the implication.
Very good question. Very good question. So this cutoff is going to be the cutoff for the density is going to be one of the main parameters of the entire construction. And essentially, you choose it by convergence. So for a given cutoff, you fit a potential. You can check its energies and forces and how well they match density functional theory or whatever your reference is. And subject to other convergences, like the amount of data, like the maximum N and L that you pick here, and a few other things, the last remaining error that you make is this cutoff. And this sounds very theoretical, but actually we do this. We reach convergence in other parameters other than the cutoff. And then you can increase your cutoff, redo the fit, and see how the forces and energies and forces become more accurate. So we actually make a very pragmatic attitude to this. And the larger you make this cutoff, the more data you have to take, the larger your fit, the more complex the function is that you're trying to fit, because the space of neighborhoods is allowed to be more complex. And that's a modeling choice. It's a very high level modeling choice. What complexity of a model do I want? What is enough to capture the physics that I'm trying to model? And that could be different for different materials, different for molecules, different for carbon, for silicon, for metals, for molecules. So this is a very fundamental choice that will then dictate what the model is good for. Very interestingly, and this is written in some of our papers and reviews, one can assess the impact of this choice without doing any of the fitting, because this interaction range, this is going to determine, this cutoff will determine the interaction radius of our interatomic potential. And one can ask, how well does the Hessian of a quantum mechanical model decay, right? So that's the second derivative of the energy with respect to forces on two different atoms. And if that decays very fast, the elements of the Hessian matrix decay fast as the two atoms are taken apart, then one can capture a lot of the potential energy surface with shorter cutoffs. So there's this sort of direct relationship like that. And we, in fact, often measure this Hessian decay before we attempt a big fit. Okay, so something that we realized much later after starting to use this descriptor is that actually it's a three-body descriptor. So how does that come about? So imagine a normal construction of interatomic potentials where you have two-body distances. That's just something that's a function of the distance between two atoms. And if you write a function that has an angle in it, then that's a three-body descriptor. Of course, these can be generalized. So a three-body descriptor doesn't just have to depend on an angle. You can have a three-body term in a force field that depends on a triangle and depends on all the three distances, or three angles and three distances of a triangle. That's still three-body. So the question is, can we understand something like the SOAP descriptor in such a way? So formally, we take the entire environment, we take the entire neighborhood. So you might think that this is a many-body descriptor as the way I've outlined it, but actually that turns out not to be the case. So why is that? Think about the density as a sum of pairs, right? So the total density is a sum of rho ij, where each rho ij is a delta function or a little Gaussian at the center, and a delta function or a little Gaussian at atom j. And rho ij prime would be another little Gaussian somewhere else at my j prime neighbor. And the sum of all of these is the total density. So if I take the definition of the SOAP vector in its integral formulation, this p vector can be written as a sum over, I can take the sum out of the density way out to the front and just write it in terms of these pair densities. And this rewriting of SOAP suggests that this is actually the sum over things, this integral term, that really only each one of these only depends on three coordinates, I, j, and j prime. And the three-body nature comes from having this product of the rows, so having two neighbors plus the center. And this product, the square that is in the original formulation, is what gives rise to the two vertices of the triangle. And so the SOAP vector can be thought of as a sum over these triangles, essentially a histogram of what triangles you have in the neighbor environment. In one of the very short talks today, this will sort of come back and be put to very good use, this idea. So everything that I've talked about is extensively reviewed in a rather pedagogical way in two recent papers in Chemical Reviews. It's part of a special issue. So let me draw your attention to that. The first one is on physics-inspired structural representations, and that's really to do with the neighbor environment and how that's defined, and that's been driven by my friend and colleague Michele Ceriotti, who has made significant advances in our understanding of these neighbor descriptors. And the second one, again with many collaborators, but sort of driven by my group, is Gaussian process regression for materials and molecules, and that's not the representation part, but it's more the how you actually use these to make potentials.
Sorry,
so
Gabor, there is another question. Mahmoud Payami, who asked if there are possibility to encounter cases where one needs four-body terms.
Absolutely, perfect, brilliant question. I don't have the drawing here right now in this slide deck, but one of the things that made us go towards the new and exciting developments that I'm about to tell you about is precisely because rather recently we have realized that three-body, knowing about all triangles in your environment, doesn't actually define uniquely the neighbor environment. And that was a bit of a shock, especially because the potentials seem to kind of work, but this was rather unsettling. So the answer is yes, very much so, and that's sort of where one is going next. But you can see the problem already, that if you have to sum over all triplets and sum over all 4 tuples and 5 tuples and 6 tuples perhaps, then that's going to be a very, very expensive enterprise. So the key is how not to have to sum over those combinatorial number of clusters. So, okay, what's new and exciting? Something that I'm not going to yet talk about today is equivariant message passing networks. I just mentioned them because they are new and they are exciting. They perform very well on benchmarks. It's kind of unclear at the moment which of their many, many tricks are actually necessary. Preliminary work indicates that not many, but they do something that is rather special. But what I do want to talk about more is high body order, exactly what the question was about. And it turns out that if you include higher body order representations, then that representation is so good that you can forget about neural networks. You can forget about kernel regression and Gaussian processes. Actually, just linear modeling using the representation in a linear way already gives excellent potentials. And this is very closely related to the ideas of Alex Chapiev. He called the moment tensor potentials, wrote down his basis functions have been arrived at through a different route, but are actually just in a way linearly related by linear transformation to the atomic cluster expansion. That's the original work of Ralph Strauss, and that's the way to go to higher order descriptors. So you can view them as a general invariant multi-body neighbor density representation, and it's sort of like a generalization of SOAP. It's very fast, it's very accurate, and it's linear. So here's how it works. It's sort of very deceptively simple. So again, you create a basis for a single particle. So that's YLMs and radio basis. You can make the radio basis depend on the angular or on the angular channel L. You can make the radio basis depend on the element, and then you take a sum, and this is the crucial bit. Now you take a sum over over all your neighbors of the radial basis functions. So this is why it's going to scale linearly with the number of neighbors. We don't have to sum over the tuples. And then in order to get the many body basis functions, you simply take a product of these basis functions. And the number of terms in this product, this nu, is the body order. If you take nu equals 1, then that's a single, that's like a two-body term because you have taken a single neighbor, you've summed over all the neighbors of a single one-body basis function. But if you take a product of these, that's like SOAP. So that's a three-body term. But you can take a product of 3 of these, and that's a 4-body term, and so on. And then the last trick, which I don't have an equation for here, is that because it's very easy to make these basis functions rotationally invariant, because they are based on YLMs, essentially using the same similar trick to how SOAP is made rotationally invariant. So what we get for this linear model is that we explicitly have a body ordered potential. So the potential is just a linear function of these A basis functions. And because they have 1-body, 2-body, and 3-body basis functions separately, you get some things for free. So for example, here's a model of this molecule, and I take away, I fit it for the complete molecule, the data is here, and I take this hydrogen away from it. So that's a very wild extrapolation test. There's absolutely no data in this fit of what happens when you take away one of these hydrogens. And what you see here is the DFT is black here, that's the fitting data. And what you see is the gap model, which is very accurate where the data is, but it's not body ordered. It's a nonlinear model of the 3-body neighborhood, which becomes a many-body model when you fit it, because of the kernel nonlinearity. It just goes back to it has this unphysical hump, and you don't even recover the fact that when you break up a covalent bond, that should cost you several EVs of energy. Here's another model, that's an Sgdma model. It's another kernel model, again, fitting everything in that molecule correctly where there is training data, but as it has no concept of the cost of a covalent bond. And the ACE model, the red here, because it has a body ordered term, it has the energy of a hydrogen atom on its own, and that's part of the specification model, if you want, it's part of the fit. And although it's not getting it perfectly right with respect to DFT, it doesn't know the energy of this radical. It's getting the order of magnitude right. It's getting the smoothness right. That when you take away an atom from a molecule, energy should smoothly go up by several levels. And we've done a lot of work in the last couple of years with this atomic cluster expansion. Here's some more evidence of transferability. So this time now on materials. So this is, I think, diamond and BCC of silicon. You training data over here, and then you expand this system. Just expand the diamond and the BCC structures of silicon with absolutely no training data there. Black is DFT. This time gap is the blue, and what you see is that yes, it goes up, but it kind of goes up and down all over the place. There's no training data here. It's reasonably smooth on the same length scale as the minimum is, because that's how kernel regression works, that you specify some notion of smoothness. But look at the ACE model. It has absolutely no data here, and yet it basically goes to the right place and much smoother than the gap model. Now, there isn't supposed to be a free lunch here, but it seems that there is, because not only are these models much better, but they're also much faster. So here's sort of a Pareto plot of lots of different models from the past 10 years. So gap, moment tensor potentials, neural network potentials. This is, I think, York-Baylor's. SNAP, the spectral neighbor analysis. That's a 4-body linear potential. And you can see, this is for silicon, you can see test RMSEs on some moderately large test set and the computational cost. And these ACE models are very, very fast. They are just polynomial models, linearly evaluated, and that gives them a big speed advantage. We see even bigger advantages for molecules. So here's a small drug-like molecule with 3 rotatable bonds. We sample their dihedral space, and this is what I'm showing you here is a particular slice in the dihedral potential energy surface. And then DFT is up here. What you see is that classical force fields are smooth but wrong. Gap and Annie, which is the leading molecular machine-learned force field, it's a feed-forward neural network using York-Baylor's descriptors that are rather similar to SOAP, are accurate-ish, but they're very unsmooth. So this sort of fuzz that you see here is the consequence of the model really not being smooth enough when when it's away from data. And the ACE model, and in fact, in this case, the Sgdma model, are both quite good and smooth, accurate. And the ACE model is the one that's transferable. So it's not tied to just a given molecule like Sgdma is, but you can because it has finite range in its neighbor environment description, and it's fast. So same sort of Pareto front here against the leading machine learning models for molecules that we've seen for materials. So in the last section, I'd like to talk about what's going to change in materials modeling. So there are new kinds of workflows, and one of them is sort of already here, and I would call it ML enhanced ab initio. So major DFT codes will have ML interpolators built into them. VASP already does, the latest version, and CASTEP is coming soon. And essentially, this allows extension of timescales. So we take systems that we can study with an ab initio code, complex chemistry, and basically automatically these MD simulations will be sped up because these systems will fit them on the fly and carry out molecular dynamics with the fitted model. They are mostly non-transferable. You can't take them to a different system. You can't take them to a new phase of the same system. It's just ab initio MD, but much faster. And then the general force field for a given larger application area is the other new tool. So you assemble a range of configurations, pressure, temperature, compositions, phases, defects, and so on. You do high throughput DFT, fit a potential, and then you iterate. And that's what I sort of alluded to already. When it's not good, you have to do more. And many of us are engaged in thinking about how these iterations should progress. How do you build up a database that's good enough for a large, wide range of applications? Then you take that potential, you stick it into LAMPS, OpenMM, GROMACS for large-scale production runs, where you discover new science. Of course, how do you know that that simulation is correct? When you're now away from the system sizes where you can do DFT directly, and that's something that keeps us up at night. So I've been speaking quite slowly, and I'm conscious of the time. So let me see what of the next 3 slides I want to show, and then we'll sort of take it from here. Let me jump to here. And that's just essentially the conclusion slides. So here's an example of such a workflow in which we build a general database. And the example here is phosphorus, which before we tried it, there really weren't general force fields. Phosphorus chemistry is very complicated. So the ingredients that go in, starting from the top right, is random structure search. So we take small unit cells and we relax them with the potential. The first one can be just fitted to random configurations, and then we iterate this process, feeding back low energy configurations, recomputed with our reference method until essentially convergence, until no new structures are discovered. Then we add to that manually constructed defect slab models. We can take the data for them from crystallographic databases. And then the last and very important part is iterative MD. So we take larger unit cells and do molecular dynamics, iterate with the potential, test them with DFT and iterate. Essentially, this is the only way to capture amorphous and liquid structures. Once you've assembled all of these, then you get a potential that can do science. So if we've done this for phosphorus, and here, for example, is the phase transition in the liquid. So at moderate pressures, phosphorus is composed of this P4 tetrahedra. This is a molecular liquid, and when you put it under pressure and about the GPa, it becomes this network liquid or fully connected. And that's something that experimentalists can measure, and there's a lot of excitement about studying that liquid-liquid phase transition. But the same potential you can go and take into a completely different domain. Here's phosphorine. It's a 2-dimensional analog of graphene, and you can take a very big chunk of it and study its, let's say, vibrational or thermal properties using the same potential. So this, I want to close by throwing up 2 ideas for new kinds of modeling questions. So one of them I would call the forward problem. So given a database of small structures that you can evaluate with the reference method, how does the accuracy of a fit, which you can control with fitting weights, determine the accuracy of material properties, large scale things that you actually want to predict, that you want to compare to experiment, that you actually care about, which is why you're doing the whole materials modeling business. And of course, the inverse of this, the inverse problem, which is that you set out to study a problem, you have material properties of interest, what fitting database is required, and with what accuracy do you want to fit it, you need to fit it to obtain good predictions for those material properties. And we know very little about this. I think I would contend nobody knows very much about this. These questions didn't really arise before because force fields were not systematic. We couldn't study these questions, but now we can, and we should. So that's, I think, is where I want to stop.
Yeah, sorry, Gabor, then maybe, since this is, there is a question by Carmen Domene about this issue of repositories. So you say, if a repository of potentials were to be implemented, considering the so many representations and descriptions used by the community, how would you envisage curating such a database? In your view, what could be the biggest challenges from a practical point of view for those setting up such a facility? And how about the challenge for the amateur modelers, users of such a platform? It's a big question, so
yeah, so I think that I would approach all of these with a lot of caution because things are moving very fast. So if you look around currently on how people define their potentials and what sort of things go into them, and you say, okay, this is what I need to capture for my facility, and you make a 5-year plan of building that facility, then in year 3 you will realize that you're out of date. And this has happened to people and has happened to projects that they went very diligently setting up repositories, databases, facilities, only to sort of find themselves not including what people are really excited about and couldn't because the way they set things up were inappropriate. So I would be very cautious. I think we're going through a stage where the development is very rapid. In some sense, from the practical modeler, the problem is not so severe because potentials, when they're made, they're published and you download LAMPs and use them. And you should, of course, validate them very carefully and rather differently than the way you validate an empirical potential, because the failure modes are very different. And the review that I mentioned in chemical reviews has a lot of text devoted to this, of how these potentials fail and how do you test them. I think that's the biggest challenge for what you call the amateur model. I wouldn't call them amateur. I would say the professional modeler, someone who actually wants to solve scientific problems. The biggest question is what's a good potential? How do you validate one of these data-driven models with 100,000 parameters? Because you can be sure that the paper describing the potential will show that it's excellent. It has very low errors for the things that it was tested for. Is that enough? I think I don't have an answer, but this is the big question. The question that should be really on the forefront of your mind. I think this takes us very neatly to my very last slide, which is where I would like to introduce and promote my absolutely brilliant students who are here, students and postdoc, who are sitting in the room with me. And I've asked them to give you 5-minute views on 4 different topics, kind of from the trenches. You know, they are wrestling with this every day, and you get to see where we are with these open questions and things that don't necessarily work easily. That's even in such a talk, I've only shown you successes. So let's see what's hard. The 4 topics that we picked. Well, the first one is how do we fit models that describe molecular reactions and in particular radicals? And that turns out to be very hard. One thing that I haven't touched on, but some of you will have picked up on or will know it from the literature, is that the SOAP descriptor and the atomic center symmetry functions of York-Baylor and many others have a very steep cost increase with the number of different elements. And so much so that some applications are in jeopardy. So James Darby will show you some ideas on how to get over that problem. And then third is a question of error bars. So many of the large scale questions on how to build databases, when is the potential not good anymore, and so on, could rely on error bars. If we could give error bars for our potentials, which some potentials have and others do not, then that could be used to design sort of meta schemes that try and answer some of these questions. And David will tell you about error bars for linear models. And then we finish off with Cass, who will show you how to take one of these models, the ACE model, and a glimpse of a vision of a larger scale workflow, which is now science and technology. How do we automatically compute phase diagrams for systems where you can't do it with DFT, they're too complex, and interatomic potentials have been just not good enough to even capture very basic features of the phase diagrams. So let's take this in this order, and I think we sort of agreed 5 minutes each, loosely. So I'll stop the share and yield the floor to Ellen.
Okay, can I check that people can hear me?
And
yeah, we can hear you.
Perfect. Let's see. Okay, thank you very much. So Gabor has very nicely introduced the very much bigger picture of modeling modeling materials and molecules, and my example will be very particular to small molecules and the radicals. And I would like to first start with the background of why of the particular application that we're having in mind, which is that we would like to predict size of metabolisms of drug-like compounds that would happen in the body. And this is really applicable in high throughput screening of novel compounds. So even before we synthesize, can we have any idea of how they will act in the body? And the cytochromes, in the essence, one, we have the protein around the reaction site, but the reactions are conserved between different isoforms. And in essence, of one type of the reaction is hydrogen abstraction reactions, which is what we're interested in. And that's the idea. So how can we model these types of reactions in high throughput on compounds that we haven't seen? And one of the main predictions of where these compounds would react is just reaction energy or reaction activation energy more precisely. But for now, we're looking at the reaction energy. So equilibrium reactants and products and differences in energy between them. And the key requirement that we have is that it has to be transferable to novel compounds that haven't been made, haven't been synthesized. And I guess the idea is that we have some kind of data that we're fitting to that has environments that we could encounter in novel compounds, even though the sum isn't, the sum of the environments and the compound exactly hasn't been seen before by the model, or the model hasn't been fitted to every molecule that we want to apply it to. And really this is a stepping point towards modeling chemical processes on the larger scale and getting to observables that we get from experiments and hopefully explaining how things are happening and having a better understanding of the processes on atomic scale. So I would like to give you a bit of a setup of what I'm doing. So I have compounds with 3 elements, which is too few for actually modeling drug-like compounds, but this is a stepping stone. A couple of examples and of the compounds that I have, and just to say that I would say it's quite a wide range of the sizes of the structures we're looking at. As Gabor mentioned, we have a kind of iterative scheme where we improve the model bit by bit. So we apply the model to a task and select places where it's not applicable or it's not performing well, and we repeat this over and over again until we get to good results, hopefully. And we fit the potential energy surfaces kind of pointwise, and the idea is that because we can reproduce the potential energy surface, therefore we can predict some observables, and in my case it's the bond association energy. So having optimized reactants and products and their equilibrium, what's the reaction, what's the energy difference between the two? And this is very much a work in progress, so I just want to give a snapshot of results. So first, we can look at the compounds. So one thing that you see is the correlation plots of how well are we doing on the stuff we're trying to measure. So looking just at atomization energy for the compounds that we have seen, so not exactly the same geometries, but the same connectivities of the chemical compounds, we see that they fall onto more or less diagonal line. But if we look at the compounds that we haven't looked, so the new connectivities, we see that we have some weird offsets. And if we look at some of them, just zoomed in, we see that they group by compound. And we can explain this by thinking about that if we haven't had an environment, a type of environment in our training set, we wouldn't be able to predict it on the whole range of compounds that would have exactly the same environment. And if we plot those environments, kind of try and visualize them, you see that there are regions on the environments and testing set that aren't covered by our training set. So of course it wouldn't work. So the first step would be to just increase diversity. So this correlation plot is for point-wise comparison, but we can look at the more complex properties like the bond association energy, and we see that these errors from the point-wise non-ideal extrapolation, it translates to some of the predictions being quite wildly wrong. And in extreme cases, so this is one of the optimization processes, we can see that we get just completely irrational, non-chemical results just from geometry optimization. That, of course, translates to the predictions of bond association energies. And one way of fixing that would be to have a semi-empirical baseline, which on one hand would have an already more physical, sensible model to correct to, but also would allow us to fit a narrower range of values. So we had some correlation plots for the DFT, and if we fit to the difference, we see some improvement. And I think the way forward is still to, now we have a sensible model baseline, but we need to still sample enough diversity to have good corrections to the baseline that transfers to many variety of Y compounds. And I think the challenge going forward is how to do that efficiently, because we can start with a couple of graphs, a couple of chemical structures that translates to more radicals, and really trying to fit the radicals kind of makes this explosion of data that we need to have and we can collect quite bad. So from a couple of different chemical closed shell structures, we can have many open shell structures. And then of course for them, we would need to sample different geometries and so on. So the challenge is to collect the data sensibly if you want to have models that are quick and accurate and could be applicable to like large scale, high throughput, general screenings. That's it. Thank you.
Unmute. Okay. That working? Yes. Okay, hi, I'm James. I'm going to be talking about compressing body-ordered atomic descriptors. Okay, so what is a descriptor? Well, the idea is that you want to describe the local environment around a given atom using a set of numbers. And you want that set of numbers to be invariant to rotations of the environment and also to permutations of equivalent atoms. And as Gabor's already said, typical descriptors that people use tend to be built up from things like distances, angles, and other sort of higher body-ordered terms. And because of this, these descriptors incur quite an unfavorable scaling as you increase the number of elements in an environment. So why does this happen? Well, for example, if I now have multiple elements, I now can't just get away with one two-body descriptor. I need basically S different two-body descriptors, where S is the total number of elements. And similarly, I can't just get away with, one three-body, the number of three-body, the length of the three-body descriptor scales as order S squared with the number of elements, and so on. And this is actually quite a practical issue. If I try to fit, say, for example, a linear model using the SOAP power spectrum, this is a sort of typical sizes for using, say, normal-ish parameters, with data set of like 10,000 structures. This is a sort of typical sizes you would expect for the design matrix. So if I've only got one element, I'm not bothered about 44 megabytes. But as I start to increase that number of elements, this like rapidly becomes a problem, and I'm not going to be able to fit these models on my laptop anymore. Okay, so this is the challenge. I want to try and compress these descriptors down to combat this scaling with S. Okay, so we started off by looking at the power spectrum. Unfortunately for me, Gabor's already introduced this. So the only thing I'm going to say really is that when you have many different species, when you go from sort of atomic positions to the neighborhood density, you have a different neighborhood density for each different element. And because of this, when you come down to, if I turn the laser pointer on, when you come down to this is a sort of a typical term in the power spectrum. It now picks up this alpha and beta index, which index different elements. And because it's got two of these elements, they both run from 1 to S, you can see that the length of the power spectrum scales as order S squared. Okay, so now what we did is we asked ourselves, to start off with, we asked ourselves a really simple question. We've got this really long list of numbers. Do we actually need to store all of them? Are they all independent? What if I only store, say, what if I give you a power spectrum, but I delete the last 10 numbers? Can you infer what they are from the numbers I've given you? And kind of remarkably, it turns out that you can. And the way to see this is to view this sum over m in a different way, and to instead view it as a dot product between vectors of density expansion coefficients, where this is the sort of grouping of terms. And the dimension of these vectors is now 2l plus 1, because this sum over m ranges from minus l to l. And the advantage of doing this is that then if you take all terms from the power spectrum, which have the corresponding to the same L index, and you group them together, you get a matrix like this. And it turns out that this matrix has a special structure. It's actually a Gram matrix. And as a consequence of that, it's low rank. So even though it's an NS by NS square matrix, the rank is always strictly less than or equal to 2l plus 1. Consequence of that means that all of the information in the matrix is actually contained in the first 2l plus 1 rows. So you only need to store those rows, and then you can use those as your compressed descriptor. And this changes the scaling from order n squared s squared to order ns. So that's great. Reduce the scaling for the power spectrum from s squared to s, exactly what we wanted to do. But this is very specific to the power spectrum. Now that we know that this sort of reduction in scaling is possible, can we come up with a more general approach which we can apply to other body order descriptors? So what we did is we went back to like, what does the power spectrum really correspond to? And again, as Gabor said before, helpfully for me, the normal power spectrum corresponds to histograms of triangles, histograms of three body terms, and where there's a different histogram for each different pair of elements. And because there's a different histogram for each pair of elements, that's where this S squared scaling is coming from. So one way we could reduce this is, instead of caring about like which element it is on both vertices of this triangle, we could only care about which element it is on one vertex. And if we do this, it involves coupling to the total density, a sort of generalized expression for the kernel down here, and then we gain a factor of s. What we saw before is that we could also get a factor of n, or reduce it to linear scaling in n. And one way we could achieve this is to now just project one of these vertices onto the surface of the unit sphere. And then if we do that, that corresponds to including this sort of projected density here. We don't need a radial basis to describe this anymore, so we gain a factor of n there. Okay, and then you can mix and match these ideas together, combine them, and you get this sort of table of different compression options. And the nice thing about this is that you can apply these different compressions to other body ordered descriptors, and in particular, and also they work for like other body orders, like higher body orders. I can apply this to like a 4-body as well, these ideas. Okay, so this is the idea, but does it actually work? So I'm going to show you the results of trying to fit some models using just these 3 descriptors here. So no radial projection, just trying to get compression with respect to S, and show you the results. So we started off by looking at a data set containing this alpacilite data set here, which contains and sort of covers the set of all structures that you can form combining the 38 main group elements with this alpacilite structural prototype. And the real thing I want you to focus on here is that the red line here corresponds to the learning curve using the full regular power spectrum, which scales as order s squared, whereas the green line, which certainly doesn't do worse, corresponds to using the compressed descriptor. So looking very hopeful here. I think at this point as well, it's worth mentioning this brown line here. So this is from some really nice work from Michele Cheriotti's group, where they tackle this scaling with S in a different way. And what they do there is they embed the elements into a lower dimensional space and then optimize the positions of these elements during the fit, their positions during the fit. So that approach is data driven. I mean, obviously it works really well, but it's data driven. So what we want to do here, we just want to stress that what we're doing here is not data driven. So that's a sort of trying to tackle a little bit of a different problem. Okay, so we move on. Different, like same idea, different data set, but this time so we're fitting lithium transition metal oxides, and instead of using soap, we're using these atom-centered symmetry functions. Take-home point is the same. Red is full soap, green is linearly scaling. Green does just as well. And then finally, we move to this high entropy alloy data set. Contains 5 elements, did a full force field fit, so we fit to energies, forces, and virials. And if you try and fit using full soap, you run out of memory before you can fit a better model. But if you use a simple 2-body plus 3-body, or if you use a compressed descriptor, you can actually fit it in memory and you get the best model. That's the best model we could achieve. I'm going to stop there. I'm sure I've run over time. Thanks.
Okay, can you hear me? I guess. Okay, hi. So I'm David, and I will talk to you about error bars for linear models. And so this is a problem that Gabor also introduced, helpfully for me. And so it's very, very desirable for us to be able to tell how accurate or how certain our predictions are in advance, so that a practitioner or a professional modeler can tell whether or not they can trust the model that we sort of provided for them, or they need to maybe tailor it to their application. So error bars are not unknown in atomistic machine learning. So in particular for Gaussian process regression, which is a statistical learning method, it's quite simple to provide rigorous error estimates. And there are analytical expressions just from linear algebra for it. And so there is a bit of a problem there, kind of the expression for the uncertainty depends on our prior knowledge of the data noise. But if we calibrate it well, these predictions will work, and you can see that they even sort of show some correlation, the true error with the Gaussian process estimate. The only problem is that it kind of breaks down a bit for sparse GPs, and this works much less clearly. For neural network potentials, we don't really have this rigorous framework for error estimation, but what you can do is you can create a committee of neural network potentials by multiple optimization runs, because neural networks are stochastically trained. So that means that you can get a committee by optimizing, maybe 8 neural networks, and then where the committee members agree, there is training data probably, so you can be kind of confident in your prediction, and where they disagree, that you can maybe say that I don't want to trust this potential. And the question is, what can we do for linear potentials? And linear modeling is something that has been studied to death in mathematics and statistical modeling. So why don't we use some of these error estimations to our advantage? And so in particular, Bayesian linear regression gives a very rigorous uncertainty quantification. But the problem is that the way we regularize our linear force fields is not really Bayesian. So we don't really use Bayesian ridge regression. And the question is whether we can generalize the ideas of Bayesian linear regression to our kinds of regularized least squares fitting problems. And the answer is yes. So you can see that what we do in least squares regression is we optimize the least squares loss function, which is basically, here this is the design matrix times the coefficients with some weights here, or this can be weights or regularization. And then this is the observation, so energies or forces, and we kind of minimize the squared distance. And then here there is another kind of regularized, so this is a rich penalty essentially. So this is like we don't want large coefficients, so this is a regularization term, and lambda controls its strength. So you can imagine that in the space of the C coefficient, the solutions, the loss is a quadratic function. So you can see that if you change the coefficients, then the loss will increase, and there will be different directions in this coefficient space. And in certain directions, like in C2 direction, the loss will increase steeply, whereas in C1, which is a softer direction, we can see that the loss, the error will not increase that much or not change that much. And then C hat is the actual optimal solution of this convex optimization problem. And the question is whether we could draw from a Gaussian that's defined by this quadratic loss surface to actually obtain a least squares committee and hence quantify our uncertainty. And so we can do that. So first we just obtain our C hat by some kind of regularization and also some maybe cross-validation or maximum likelihood. And then we compute the corresponding covariance matrix that's defined by this quadratic loss function. And that has this form where we have our prior, which is this beta n would be a prior noise estimate. And this we came up with a way of because we don't really have this noise that if you do a molecular quantum chemistry, then your actual quantum observations are not very noisy, but we still need some scale. We need to set some scale for our covariance, and we can do that by saying that our noise is proportional to our accuracy on each of the training points. So given a mean, we know how accurate we are, and if we are very inaccurate, then we say that in that region we are very uncertain. And this way we can calibrate our covariance matrix to give us nice committees. And then we can sample from the resulting posterior to obtain a different coefficients. So here it's for ACE, for example, but this can be used for any linear model. And we can illustrate this approach in 2D. And just very quickly, you can see that if we have a few data points, then this way we can get a nice fit where there is data, and then our uncertainty explodes where there isn't data. And then as we add more and more data points, we become more and more confident. And what's more is that we can also, using maximum likelihood, find what is the optimal basis set for a given data. And then we can also just a few example applications. So we can create force fields using these linear models. And then we can look at things like dihedral torsion scans. This is something that's crucial for correct sampling of in biomolecular applications. And you can, for example, here see that this is a histogram of training data along this dihedral angle. And you can see that there are a lot of training data points around here, and not so much around here and here. And you can see that here I'm showing the uncertainty, and the uncertainty peaks where there is a dip in the training data, and you can see that the uncertainty has a minimum where we have a lot of training data. So in some sense, we can see that our method does work for force fields. And what's more is that we can even predict quite nicely the errors. So we can see that the relative force uncertainty, so this is a fit on a large and very diverse hydrocarbon data set. You can see that the relative force uncertainty correlates very well with the relative force error. So with that, I'd like to thank, and just thank for everyone. And there is ACE.jl and IPFitting.jl, the two codes implementing what I was talking about. And this is a very recent paper that we just published. So if you're interested in linear atomic cluster expansion force fields, then please check out. Thanks.
All right, hello everyone. Can everyone hear me? I hope so. So today I will talk to you briefly about an application of the atomic cluster expansion as well, and more specifically about molybdenum, niobium, tantalum, tungsten, which is a high entropy alloy. And these types of alloys are generally sort of described by at least having 4 components and having close to equiatomic element composition, so relatively equal proportions. And these particular high entropy alloys are interesting for industry in particular because of their excellent properties relative to more standard alloys that are now being used in industry. So for instance, the things they have much better than other alloys currently on the market is better strength to weight ratio, better fracture resistance, tensile strength, and corrosion oxidation resistance. And people are thinking about using these particular alloys mainly for additive manufacturing and alloy design. So say you want to maybe print some interesting component, as you can see here on the right. What people are now trying to do is print them using these large industry scale 3D printers. And in order to do that, people want to understand actually what these alloys do, especially in the melting temperature, right? Because you may have some particular alloy or some different composition. And how does that sort of what kind of phases do form after you've gone from melting into the sort of the first high temperature phases, and what are these properties, and actually what is the proper composition perhaps to create your models given the properties actually you do want for your system. So, and I think nowadays there are not many very good ways of actually modeling these high temperature phases, and particularly these transitions are very important, such as, for instance, the melting temperature. So what is, for instance, the melting temperature of these sort of high component or high entropy alloys, and also more importantly, there are a few order-disorder transitions, as you can see here on the right, at lower temperatures, where maybe on the right you see some disordered phase, which is generally more a high temperature phase, and an ordered phase, as you can see here, if you think about this in sort of periodic boundary conditions, where you have some close range order. And these has effect on mechanical properties and like strength to weight ratio or tensile strength, and these other properties that people don't really understand too well yet. And actually running this through DFT is very expensive. So this is where we are going to use the atomic cluster expansion to create models that can actually model all these different types of alloys and on different in different phases, including the liquid, and actually use it to simulate it. So we're going to use the atomic cluster expansion, and what I did is I created a database of 36 atom cells and with 97 random BCC alloys. So this particular high entropy alloy is a BCC alloy, and 151 liquid configurations sampled at some high temperature. And I used those to set up a database, which I then fitted my ACE on. And what you can do actually is because these ACE models are linear, you can actually take a Bayesian approach, a bit like, or actually very much like David mentioned in the previous presentation. And one thing you can also do is Bayesian model selection. And what that sort of does is you can determine what is the most probable model given your data. So the way you do this is you actually determine the marginal log likelihood given your database and your model, which sort of combined give you the marginal log likelihood. This is very textbook. And sort of the idea is that you want to maximize this marginal log likelihood because that is sort of the model that is most probable to describe your data. And what you see here on this plot on the right, you see n equals 2, which is a 3 body. So n here is the correlation order. So if you think about a central atom and having 2 neighbors, that effectively is a 3 body. You can see that by increasing the model complexity, and by increasing the model complexity, I mean polynomial degree, right? So actually adding higher and higher term polynomials, you can actually see that initially the marginal log likelihood increases, and actually at some point comes to a maximum here, which is degree 16, and then beyond that it actually decreases again, which effectively the marginal log likelihood is telling you that your model is too complex for the database you're trying to describe, and actually you should actually scale back because you're really starting to overfit effectively. And what is perhaps more interesting here is that actually adding higher order interactions, which is n equals 3, which is a 4 body, right? So central atom for 3 neighbors effectively is a 4 body in more traditional body order terms, actually has lower marginal log likelihood. And what the database is telling you is that you actually want to use a simpler model in terms of correlation order to describe the data for effectively also when you look at the performance here, because yeah, so the right model here, if you look at this marginal log likelihood, is a degree 16, polynomial degree 16, n equals 2, or a 3 body potential. What you can then do is you can just set up a very simple linear model after you've chosen your model, which you can then fit in about 40 minutes using about a gigabyte large design matrix. It's not very massive. And actually the performance of this particular potential was 1.4 millisecond per atom for a force call. So that's reasonably quick, and it allows you to really simulate very large systems. And for this particular fit, the training errors are shown here, where I show you the errors on the liquid configuration, training errors I should add, which are much higher than the random, but I did that because I adjusted the weights, and this weights is still very much an open question on how you should do that properly. And I think one perhaps way to look at it is maybe to think about even relative force errors. So if you look at these errors on the forces, the liquid is much higher than the random bulk alloys, but actually in fractional terms, you have perhaps 6% on the random bulk structures and 10% on the liquid, which may, to me, seems reasonable, where you have a fractionally a worse accuracy on the high temperature liquid and a lower fractional error on the random bulk alloy. But actually, when you look at it in absolute terms, there's a factor of 3, but actually in relative terms, it's much less. So anyway, what we can do to use this potential is we can actually use it in nested sampling. So nested sampling is a way to effectively integrate the partition function. So what we do is you have a whole bunch of walkers. You start at very high energies, actually in the gas phase, and you use them to decorrelate and really integrate over all configuration space and determine the density of states over the whole from the whole system, from very high temperatures all the way down to the global minimum. And by doing this, by determining the density of states, you can calculate the partition function from which, as people know, you can derive any thermodynamic quantity, such as the specific heat capacity. And the heat capacity, from the heat capacity, we know that it's sort of a signature is a peak around a first order phase transition. And these first order phase transitions can be liquid to solid and solid to solid. So if you look at what's happening here is that we first see a big peak around just below 3000 Kelvin. And from also, I verified this is actually the melting temperature, because if you run it at hotter liquids, you see the system starts to melt. The CalFAT, which is sort of the state of the art now for determining melting temperatures for alloys like these, also indicates a melting temperature around this temperature. But then actually, when we go on lower and lower energy levels, we actually see we can also find other solid to solid phase transitions, which are also first order phase transitions. And you can see here this sample where you see a more random alloy where you don't see any sort of short range order. And here you see some order where you can see these lines of these rows of same species of atoms. And this could be useful for people to maybe start modeling and actually understanding which phases are stable at which temperatures. And when you're printing, for instance, when you're using the 3D printing, you can maybe understand which phases you want or don't want, or maybe look at cooling rates and understand actually what you're printing. And DFT is not actually used. You can't use DFT for this because we have to run about 1 billion force evaluations. And if you do that using DFT, that will take a very, very long time. So this is why we need these very fast millisecond per atom potentials. All right, that was it. Thank you.
Okay, thank you very much. And if you can stop now the screen sharing, we can now move on to the Q&A session, where I remind you, all of you can participate. You can simply, using the Q&A channel, indicate that you want to ask a question, and we will unmute you, and that will give more possibility of a more direct interaction. So there are actually 2 pending questions that were raised during the talk. You can start for those one. One is by Andrei Stelmacht. I don't know if it's possible to give unmute him.
Yeah, could you hear me?
Yes, we can hear you.
Okay, thank you for a very, very nice talk. I have a question to Gabor. Maybe I can wait a few seconds.
I'm here. Go ahead.
So I'm wondering if it's possible to combine first principles force fields with classical force fields within a single simulation. For example, if one wants to study an interface between an inorganic material and some organic solvent or water.
That's a very interesting question. I think that with the rise of body-ordered force fields, machine-learned force fields, I think it's not impossible, but I haven't really seen people do it. And the reason, what makes it hard, is that when you come to fitting the machine-learned force field, you have to have a reference. And that reference includes everything. And now you're going to have to then subtract your empirical force field from that reference in order sort of not to double count. And the question is, how good is your empirical force field? It may be good enough for your purposes, for macroscopic properties, that you want that part of the system that you're describing with the empirical force field. But if it's not giving you energies and forces that are a reasonable approximation of the reference, you're actually going to make the fitting task much, much harder when you subtract an inaccurate force field from a reference. So could you then kind of coarse grains as part of the system which you are less interested in during the fitting process? The problem, the parts of that you're less interested in are not remote. So if you have spatial separation, then sure. And people have done QMMM, where they swap the QM to ML, so ML, MM. Mm-hmm. And you have spatial separation and no covalent bonds between the parts of the system described by anytime you can use QMM, and you can always use MLM, but I think you'd be hard pressed to simulate, lithium transport through a solid where the solid is described by an empirical potential or something like that, because there you don't have this strict spatial separation. So I'm not saying it's impossible, but I think it's very hard to set it up sensibly if you don't have spatial separation.
Okay, thank you.
Okay, thank you. So there is a second question also by Mahmoud Payami. Again, maybe he can phrase it live. So is Mahmoud unmuted?
I can read his question.
Well, I mean, yeah, it was just in case he wanted to rephrase, but yeah, you can read it and then reply, and then if there is anything else, you can.
So Mahmoud was asking whether.
Do you hear me?
Oh yes, now we can. Why don't you say your question?
Okay. Thank you for nice presentation. My question is that on three-body terms on local environment or more body terms, if the atomic interactions are short range, I think we may need four-body terms, but if the interactions are long range, we can increase the radial distance to cover different environments. Is it true or not? Thanks.
I think that there is a relationship generally, one hopes actually, that longer ranged interactions are fewer body. But this is it's not necessarily a good direction, because increasing the range of these neighbor environment representations is very expensive. So there are other better ways of incorporating long range interaction. So in particular, of course, there's been a lot of work in trying to bring in electrostatics, so Coulomb interactions. And look, the functional form, it's 1/r times some local property. So that it seems to me that not using that fact that that the interaction has a 1/r scaling is something that you should use the knowledge that you have. So I think just trying to make the machine learning program or algorithm pick up the 1/r when it's there is a bit of a false task. But beyond that, I think within the range of 3 angstroms and 8 angstroms, there is some effect. I don't think it's been well characterized, but there is reason to believe that a longer range interaction is fewer body. But I'm not aware of rigorous results or even numerical experiments that have shown that.
Thank you.
Okay, thank you very much. There is now a question by Amin Alibakshi. Which again, I guess you can read if Amin cannot talk. So maybe you can read it, and if he can join, he will do that later. So thanks for your talk. Where do you see the future of machine learning force fields you presented today based on subvariance, especially in terms of the ability of extension to systems which contain multiple atom types? And what are the challenges and what would be the directions toward the solution?
Okay, so I think that SOAP and ACE behave similarly in this respect. The future of SOAP is to be generalized to these ACE type force fields. But there's no problem doing 2 or 3 different atoms. And I think needs to be done. And we have many force fields with 2 and 3 different atoms. But with many, many different atom types, so 6, 7, 8, or 38, like what James showed, that really is a problem. And I think the solution, after James's work, I'm convinced that that's the solution, is that these just increasing the body order and the number of basis functions with the number of elements is not right, because you don't have to, and these are vastly over complete representations in that sense. And the kinds of compressions that James showed, I think, seem to be very, very effective. So I think that's what I'm hoping that that's what everyone will do. That's what we will do. And it applies not just to SOAP. So it applies to Weyl-Parnello symmetry functions. It applies to SOAP. It applies to any neighbor density based representation, FCHL, anything that works with the neighbor density.
Okay, we have then now a question by Gianmarco Riganese.
Yeah, good afternoon to everyone. Thank you very much for the very nice talks. I had a kind of practical question, Gabor. You mentioned that so VASP is implementing already something like that, and that CASTEP is going to implement it. I was wondering how you see that. I mean, is it the DFT code that needs to be connected to the machine learning potential algorithm, or the other way around, so the machine learning algorithm that call the DFT code to get more information?
I think that there's legitimate use case for both, right? So in VASP, you have quite a tight integration. So they have what is a very small variation on SOAP gap that they've implemented into the VASP code, and did a lot of work on parameterizing it. So make sure that the hyperparameters are reasonable. And so you can use it as a black box. And that's certainly one route. What we're experimenting with in CASTEP is that there are sort of 2 codes, each sort of standalone, but there's communication between them. So it's very easy to swap out the machine learning interpolator or to adjust its parameters. But you submit the simulation from the DFT side. I think that whether you want the DFT to drive it or not depends on how you envisage the simulation to run. So, for example, if you're very happy to always be able to always confine yourself to system sizes for which you can do a few DFT calculations, and you're using a very large supercomputer where you've optimized the DFT, then making that the driver makes a lot of sense. Whereas on the other hand, if you want these DFT ML codes to really just get you started and generate an ML potential, which you're then going to take out and run on much bigger systems where you're not expecting to run DFT, then you may want it the other way around. So that's more closer to assembly of a database where the ML, the workflow driver is on the outside and calls the DFT every now and then, but is doing that, assembling a database, fitting a potential, which you then use with some MD code. So I think it depends a little bit on the vision for the simulation. I think both will happen.
And so for CASTEP, you're developing the 2 possibilities basically to go from one to the other or to the other.
Yeah, I mean, with CASTEP, we're working on the data on the CASTEP driven one, because we're sort of thinking of our users as, I'm a CASTEP user, I would like to run faster, but I don't know, I don't want to bother with databases and manage the whole potential business. I don't want to know about that. Then that's one extreme use case. The other one is you're building a potential, and that's a much more complicated workflow. I don't have a very generic solution for that. I think lots of people are wrestling with that.
Thank you very much.
Thank you. So there is now a question by Michele Ceriotti.
Okay, sorry, I needed to unmute. So yeah, I wanted to ask, and perhaps directly to James. So why not data-driven? if it can be much more effective and you don't actually lose any accuracy. And I'm not referring just to the 2018 paper in which we were trying to compress only the elements, but the optimal basis in which for QM9 we can really cut like by a factor of 20 the number of SOAP features that you need to compute just because you compress simultaneously radial and elemental channels.
I've not actually seen your more recent paper on the optimal radial basis, but sort of the general the origin of why we're thinking about non-data driven compression is we're thinking about storing descriptors in databases. And then in that case, the sort of optimal data driven embedding for one situation or like one model predicting one property might be different to another. So that was sort of the origin of being interested in non-data driven compression.
I see. So basically having a permanent version, but in a certain sense, isn't it still linked to the, it's in a certain sense still linked to the data that you are working with, in the sense that the level of compression that you might be able to afford for a certain system might be very different from the level of compression that you might be able to afford if you add, imagine for instance, you have a model that is trained for pure elements and then you add just a new phase in which they come together in a different way, and you might need you might still need to change the way you compress.
Yep, I can definitely see what you're saying there. So I guess one point maybe I didn't stress enough is that if you store, say, only this 2l+1 rows as part of your compression, that's actually like a lossless compression in that sense. So there's no, if that makes sense, there's no sort of, if you use that, go down that sort of route, there's no decision to be made in terms of how much you compress. But yeah, I totally take your point.
Thank you.
Okay, thank you very much. I just have a curiosity before we move on. I mean, Gabor, you started the presentation by referring to those two seminal papers, 2007 and 10, and how they have delivered and brought us where we are now. I don't know if in view of what has happened and where we are, you would be willing, or you have an idea of what would be the next challenge, or how do you see now the next years, not decade, but in the next years, mostly evolving or delivering from where we stand?
I think that there's a lot of work starting from about 5 years ago and going on now about self-consistency, being in electrostatics, not just as a baseline. Actually, Georg Wehler has done a lot on that himself, but I think there are others. Michele Ceriotti just spoke, Stefan Gödeker, and those are all, I view them all as kind of experiments, proofs of principle, but we need to have a similar shakedown between those methods as we have done between representation. So I think having self-consistent, charge self-consistent ML models is something that's going to happen in the next couple of years. That's one. I think that's one big direction. Another one, which we can't. I've been trying to avoid it for many years, but really I can't, is the challenge of making bioorganic force fields. So actually going and replacing as appropriate, when it's appropriate, the force fields that have served the biosimulation community for 30 years, served them very well. How do we do that in a way that's robust, reliable, efficient? I think that's, again, there are sort of proofs of principle and experiments, but not something that you can go and simulate the protein with. And that's not the next 2 years, that's the next 5 years. In research and development, when you say 5 years, that means you don't know how. So yeah, I think that's the next big challenge. I think for materials, we've delivered, and for few element material problems, we know what to do, but not for bio.
Okay. Well, thank you very much for these engaging presentations for the whole team. And I think now it's good to move to the last speaker of this first part of today's session. This is Sylvia Bonfanti from Università degli Studi di Milano, and she will be talking about machine learning and metamaterials. So Sylvia, now the floor is yours.
Okay, can you see my screen? I hope so.
Yes, we can, yeah.
Okay, so thank you very much for the chance to be here, and good afternoon, everyone. So today I will talk about our new algorithm that automatically design metamaterials actuators. And also I will explain how to employ machine learning to study metamaterials. So first of all, I would like to start with a brief introduction on metamaterials that are one of the subjects of my research field. And especially we will see in the course of this presentation how metamaterials are going to change the concept of materials as we know them now. But now let's start by asking ourselves what are metamaterials. So meta derives from the Greek and means beyond, but beyond what? Beyond traditional materials such as the wood of our desk table or the glasses that we find in our kitchen. So these are all examples of ordinary, conventional, traditional materials. Metamaterials instead have something more. In particular, they are materials that possess an internal structure which is made up of cells, as you can see, for example, here. And it is properly the geometry of these internal cells that gives them outstanding properties and functionalities. There are many kinds of metamaterials. They can be optical or acoustic or electromagnetic, but here we study the mechanical metamaterials, so the ones that can perform a physical mechanical response. In particular, we will tackle mechanical metamaterial machines. So these are kind of metamaterials that can perform movement or change shape. For example, here we can see a door handle, which is made up of entire metamaterial, which is 3D printed, and the cells, the arrangement of these cells is not random, but it is placed in a way to allow this rotation and open the door. So these are very promising materials. In fact, they are rapidly expanding in many different sectors, from aeronautic to automotive. For example, here we will see that the air companies are now working in order to try to substitute the full structure of the plane with these metamaterials in order to reduce the weight of the plane. And then they are, for example, used for medical application in soft robotics, fashion, and so on. So they also are very attractive because they can range from a different length scale, from micro scale to up to the macro scale. So now let's come to the problem of the main problem of metamaterials, which is the bottleneck in their design. So how can we find the correct recipe to design the internal structure of this metamaterials actuator? How do we proceed to perform this movement? Actually, this is a problem. In fact, mainly so far, this metamaterial architecture have been constructed by trials and errors, and even experts such as scientists and engineers bump into this problem. So here is our solution. Why don't we use artificial intelligence and let the machine design the internal structure of the metamaterials? So in this case, we mean that our algorithm that I will explain in a moment should help the design process in order to automatize the production of this configuration. And in this way, the goal is to get the movement of the actuators that we desire, or even a particular specific property. So this is the schematic of the structure generator automatically. This is a brief overview, then I will explain in detail. So basically we start with a configuration. In this case is a full configuration from a triangular lattice, and then by applying the algorithm we remove and add the bond by also selecting a region of input and output nodes, and we will minimize a cost function. Then we validate our results also with finite element simulations, and we can even 3D print our structure. So the optimization process is efficiently realized, coupling the optimization algorithm with discrete element simulations, as I explain in a moment, and suitable trained deep neural network. So here we come to the definition of a concept that will be helpful in the next slide, and it is somehow central. Is the concept of efficiency. So how well the metamaterial perform the assigned task. And in particular, this concept depends on the specific problem. For example, we defined two types of efficiency: direction-based and force-based. For the direction-based efficiency, the search of the metamaterial configuration is focused on the maximization of the output displacement toward the desired direction. Here, T input and T output are the versor of the direction, I are the input node, and J are the output node. And 0 means the position, the rest position. Instead, for the force-based efficiency, we have that the exerted force on the input nodes is propagating to the output nodes towards the target direction. And this type of efficiency is specifically needed when we want to integrate our actuator in a larger mechanism. So in this case, what we do is that we apply a constant force in the input nodes and measure the output nodes by means of the springs. So in all cases, we maximize the efficiency by minimizing the cost function delta, which is equal to minus eta. And so now let's come to the modeling of this metamaterial. So I said before that we use the finite element methods, so we can, this is one possibility, but actually this is very long to converge. So, and here we want to try and test many solutions. So we proceeded implementing a discrete element model to model the metamaterials, and this one is a good compromise between the speed and the reliability. In particular, we constructed this energy function, and we are going to minimize this one. It is composed of two terms, these phi2 and phi3. Phi2 means the stretching of the bonds, is the terms of stretching, which depends on two nodes, I and J, in this way, while instead the phi3 is the bending term, corresponding bending term, depends on three nodes and on the angle among them. And this is actually the feature which is the one which is near to the real beams for their modeling. So then we proceeded with our optimization scheme that is nothing but a Monte Carlo algorithm, and which is coupled with this discrete element simulation. We start from our initial configuration, and then what we do is that we add or remove a beam, we get the new configuration, and at some point we displace the input nodes. We perform an energy minimization of our function through fire scheme. We measure the displacement of the output nodes, and then we can evaluate the efficiency and our delta trial. If delta trial is less than delta zero, we accept the configuration. Otherwise, we accept it with a probability P, and then we continue the iteration in this way. So I already anticipate you that the machine-generated structure wins with respect to the human design ones in terms of efficiency. And now we are going to see how. So for example, let's focus on two simple type of displacement-based mechanism. Let's imagine this box is our initial lattice configuration. So that we define an input and a desired output direction. In this case, it's orthogonal. In this case, it's anti-parallel. So now we will launch the algorithm that I showed you before. And this is what is going on. So this is the input direction, which has been displaced. And this is the output that we require that should be minimized to follow this direction. So the algorithm move and place and remove beams till it finds a solution. Okay. So here is the plot of the efficiency as a function of the Monte Carlo step for this orthogonal movement that we saw before. Each of this curve is obtained with a different initial random seed, and we report only the efficiencies corresponding to the accepted Monte Carlo steps. And we can see that this efficiency tends to evolve in steps, and they are interdispersed by noisy part and by this plateau. You see this here, the plateau. So it means that this step occurs when a mechanism that engaged the desired response is triggered, while instead the plateau indicates that there is no changement in the efficiency when adding or removing a bond. So here we see that we compare the human design structure with the machine-generated structure for the orthogonal movement. So here one note is that the human design structure was designed before having seen the solution of the computer. So, and here we can report their efficiency in terms of displacement. We will see that the efficiency of the machine design is higher than the human design. Here instead is also the example of the anti-parallel movement. Again, this is the human design and this is the machine design. The color bar here represent the stress. So we see that in this case the stress is located in this region, while here is more distributed. And these are the 3D printed structures. So then we ask ourselves, okay, these are structures that are generated starting from a triangular regular lattice. What about starting from initial random configurations? So we actually construct this random metamaterial configuration starting from random configurations of disk brought at mechanically stable jamming point, compressing a simulation box, and this is a standard protocol for jamming algorithms. Then we connect the center of each particle disk, joining it with a bond, and we generate this random initial configuration. And by doing so, we are sure that we have stable mechanical properties. Then here, let's see the results of the periodic versus random lattice. So here we apply again input and output in the same region. The bottom are the random configuration, and we have here two different input displacement. So if we look here at the plot of this efficiency as a function of the input displacement, we can see these two particular configurations. So in the small input displacement, the random lattice based metamaterials outperforms the one obtained from the triangular lattice, while instead, when we go at a large displacement, the two lattices show similar efficiencies. Okay. So here instead is another example of a force-based efficiency. In particular, what we compare again is the structure generated by humans. So this is a conventional pliers, and the machine-generated structure. So in this case of the force-based efficiency, what we require is that we have high spring stiffness in the output region and small input force. And once again, we see that the machine design pliers are more efficient, more than double efficient than the human design one. This is not really a beautiful configuration, but for sure is more efficient. And here, due to the symmetry along this axis, we could only simulate the upper part and then mirror down the rest. At this point, we ask ourselves whether we could predict the efficiency by machine learning without running our discrete element simulation. So we use the static images of the configurations to infer the efficiency without simulating all the minimization. We train a deep neural network, a convolutional neural network, to perform image regression and predict the efficiency of a configuration from a given image. So basically what we are doing is that we are coupling the optimization algorithm with a trained deep neural network. We used a large number of configurations equal to 10 to the 6, and we achieve an accuracy of 0.966 that you can see here. So this is the density plot of the efficiency. These are the efficiency obtained from the discrete element model, these from the convolutional neural network, and we see that the CNN model is able to predict the discrete element model efficiencies values very well. Okay. And then one step further, we constructed functional heat map displaying the predicted increase or decrease of the total efficiency when the structure is modified. So in particular, we compare this CNN model with discrete element model. And here we can see that the blue correspond to regions that lead to a lower efficiency, while the contrary is shown in red. So what can we see? We can see that this functional heat map generated by the convolutional neural network are in very good agreement with those generated through the discrete element model by removing a bond in this case and measuring the efficiencies. And then one step further, we trained our convolutional neural network over 172 bonds, and we used to infer these heat maps in larger size structure, this one, which have 694 bonds. And here, once again, we compare the result of the CNN with the discrete element model. And this time we see that the agreement is not so good, but still acceptable. And so we can say that our convolutional neural network will predict the efficiencies and can tell us the increase or decrease of the efficiency when we remove or add a bond. So then we pass to real life via 3D printing. These, I haven't mentioned these, but actually these kind of actuators are very important, for example, for industrial application, because they can substitute all the complexity of the traditional actuators, which consist of many components. These instead are consisting in one single block, which is 3D printed. So this is an example of how an algorithm that is in some computer simulation, which are generated in the computer, can be arrived to the real life with the 3D printed actuator. And actually, we patented this method in 2019. So this was a bit the roadmap of the project. In March 2019, this project won a proof of concept of the ERC. Then we got the Italian patent. We published some of these results in Nature Communication. And then this year we proceeded with the 3D extension of this algorithm, and we explored the new mechanism. So here is the reference paper that I'll explain you today. And also you can find the code if you want to implement or use it. And here is the extension that I mentioned you before. We try to design this time a metamaterial that rotate under compression, and this is the result of the machine generated structure. So in principle, you can design whatever actuator you have in mind. It's enough to give an input and an output or many output region. So this is the team, which is guided by Professor Stefano Zapperi, which is the project leader. Then there is Roberto Guerra, researcher at the University of Milan. Then there is me, Frances, Lorenzo, and Daniel. And so I thank you for your attention.
Thank you very much, Sylvia. Now we have time for the Q&A. I remind you, you can simply indicate in the Q&A channel that you want to ask a question, and then we will unmute so that you can pose the question yourselves. So there is one question already by Mahmoud Payami. I don't know if we can unmute him, like he can pose the question.
Do you hear me?
Yes.
Thank you, Sylvia. I have a question. Can you impose a constraint on mass density of the metamaterial designs? For example, I want to design a metamaterial with 1 gram per cubic centimeter density.
Yeah, this is possible to do. We have not implemented this solution, but yeah, the code is you can modify the code by introducing yes, other constraint. For example, this one of the mass, or for example, you can even tune the spring stiffness if you want to, say, change a material type. You can just tune, make that the spring are different in different region, for example. So you can really use it with the different constraints. So it's good.
Thank you.
Thank you.
I had a curiosity. You mentioned at the very end that then you expand the approach to include this chirality. So when you introduce this new type of symmetry, how much do you then need to change the whole approach? Because in a way, you need to introduce that as a kind of constraint, or it's simply the generating of the output with the right symmetry that it's enough to extend the machine learning approach?
No, you need to take into account for also the dihedral term in this case, which is not so easy at the first attempts. So it took a lot of time for us. But then, you can impose the symmetry. In this case, we imposed a rotational symmetry along the z-axis, so to get the rotation. And for this particular 3D rotation, we did not perform the machine learning yet, but this can be for sure a good idea to implement.
Okay. And also then in the combination of the two schemes, when you say that you exploit the machine learning, how many data do you need? I mean, is this something really that limits the analysis, or just the type of standard finite element methods produce enough configurations by itself to be easily adapted and exploit the machine learning scheme?
No. We can actually, in the second part, if I can go back, yes. So here in the second functional heat map part, we extended the data from the smaller lattice. So in this case, the machine learning is used to infer prediction on bigger lattice sample size, so that we don't have to simulate them anymore. So the goal, the final goal would be that the machine learning can give us a prediction even on a structure that it hasn't seen. So this was a first attempt, of course.
Okay. So there is also a question by Frank Smalenberg.
Hi, can you hear me?
Hello, yes.
Thank you for a nice talk. I was wondering, you showed the trajectories of your Monte Carlo simulations where you sort of optimized over time. And there seemed to be quite a lot of variation in the final efficiency. If you run many runs, do you eventually end up with very similar structures for the best case scenarios, or are there structures out there that you just don't reach?
Indeed, we were searching for families or categories of movement, and this is what we found. So when we had in the same range of efficiency, we found more or less that the structure, the mechanism is similar. But then we were not able to classify all these families. So maybe here there is more work to be done. But I have in mind, for example, the clusters of Lennard-Jones, where you can find many minima, and this reminds me, this plot reminds me that, but still we haven't found the families, let's say.
No, that makes sense. It seems indicative of an energy landscape with many local minima, and finding the best one is difficult, but it's already interesting that you sometimes end up in a class of ones. So it's interesting to see. Thank you.
Thank you.
Okay, thank you very much. I don't see any additional questions, so maybe this is a good point to stop. Thank you very much, Sylvia. We are reaching the end of this first part of today's event. I remind you that then for those who have registered, we can continue now in Gather. And as I said, there will be a new installment of this series just before Christmas, and you can also see previous sessions on our website. So thank you very much, and stay tuned for our future activities. And you can follow them by registering to our webinar mailing list. Thank you.